Hi, everybody. Welcome back to the Feynman technique. Today we're going to be deriving what I believe is an original proof that the sum of the reciprocals of the odd squares is equal to pi squared over 8. And we will be doing it by showing two things. We will be doing it first. We will be showing that the imaginary part of the integral from 0 to infinity of arctangent of ix over x dx is equal to pi squared over 4, and that the imaginary part of the integral from 0 to infinity of arctangent ix over x dx is also equal to 2 times the sum of the reciprocals of the odd squares. Okay, so, what one should we do first? Well, neither. Actually, what I'd like to do is let's define a function of t equal to the integral from 0 to infinity of 1 over t squared x squared plus 1 dx. And if you evaluate that, I believe you are going to get pi over 2t. Yeah. Okay. So we'll just go ahead and state that right off the bat. So we have this. Okay, great. So what does this mean? Well, I'm going to do something that I haven't done on this channel before. What I'm going to do is these are both functions of t. So what I'd like to do is integrate both sides from a to b with respect to t. So let's do that on both sides. Integral a to b with respect to t. All right, so from here we can on the left hand side here we can switch up these integrals. We can use Fubini's theorem. So instead of integrating from 0 to infinity dx first, we're going to integrate from a to b dt first. Now, there's no problem with doing that. I'm not going to get into why you're allowed to do that. It's fairly straightforward. In this case, you are allowed to do that. So now let's go ahead and evaluate this integral right here. I'm just going to go ahead and plug that into online integral calculator and I'll be right back. Okay, so what this is equal to is this. It evaluates nicely to this, and that's not difficult to show. It's pretty straightforward integration. I just didn't feel like doing the steps here on this video. And this integral right here is going to be equal to pi over 2 times the natural log of b. Hold on. Natural log of b minus natural log of a. Okay. So what this gives us is this. This is equal to this. Oh, no, 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 no. That's totally wrong. Okay. We started here. So this means that the integral from 0 to infinity of this dx is equal to this. All right. There we go. All right. So what were we trying to show? You know what? I'm gonna delete these intermediate steps right here because this is really what I was interested in showing. Okay, now we're trying to show that the imaginary part of this is equal to pi squared over 4. Um, all right, so what does it look like we have? It looks like we have, um, well, let's just plug in b is equal to I. Okay, let's just plug in b is equal to I. We're not going to plug in anything for a because a in this case is going to be a real parameter. So we're just going to plug in I or b. Okay, and then we want to take the imaginary part on both sides. So let's go ahead and take the imaginary part on both sides. While taking the imaginary part on this side, we no longer need this part right here because this is going to be purely real if a is a real parameter. All right, and likewise, if a is a real parameter here, we can get rid of that. Okay, so from here, we have that the imaginary part of arctangent ix over x from 0 to infinity dx is equal to the imaginary part of this. Now, I is e to the I pi over 2. It has other values, but we're just going to use the principal value. Taking natural log and e composing natural log with e is just going to give you I pi over 2. Taking its imaginary part, we just end up with I pi over 2 here. So we get pi squared over 4. Great. So we've shown that this is true. We've shown that the imaginary part of that is equal to pi squared over 4. Now our goal is to show that not only is it equal to pi squared over 4, but that it's also equal to this sum. And that's going to be a little bit more difficult. Okay. How should we do this? Well, let's go ahead and start at the very, very beginning. Okay. We know this. We know that 1 over 1 minus x is equal to the sum as n goes from 0 to infinity of x to the n. Okay, well, what else does that mean? Let's just replace our x with a negative x squared. So that's going to give us 1 plus x squared. Now don't forget we replaced it with a negative x squared. So we're going to get a negative 1 to the n times x to the 2n. Okay, great. Well, let's anti-differentiate both sides with respect to x. We can do that. dx, and then integrate dx. Now, we can switch the integration and summation notations there, and then we can bring out this negative 1 to the n. Anti-differentiating this is going to give us x to the 2n plus 1, 2n plus 1 over 2n plus 1 plus c. Now we need these to match up. Well, this gives us arctangent x, right? That's the antiderivative there, arctangent x. We need this to match up for all values of x. So we'll plug in x is equal to 0. We get 0 on this side and 0 plus c on this side, implying that c is equal to 0. So that is true. Okay, but now there's a problem. This formula right here only, you know what? I'm going to back up a little bit. I'm going to back up to this part right here, right? Okay, so this is true, but it's only true for, let's see, and I'll show you. Let's bring out our little graph right here. And let's show that 1 over x squared plus 1 is indeed equal to this. Now, it doesn't like, Desmos does not like infinities inside of sum, so we'll just go to 10 or maybe 100. And you can see that this is going to hold for the absolute value of x less than 1. So we have a problem now. This formula is only good for the absolute value of x less than 1. Now, our bounds of integration, we're letting x go from 0 to infinity. So whenever we figure out our arctangent x sum, it's only going to be good from 0 to 1. So how do we fix that? Now, there's a lot of ways you could fix it, but what I'm going to do is this. Let's open up the Microsoft whiteboard, and I want to show you something. There is a way to develop Taylor series that basically fill in. If our original Taylor series was only good for absolute value of x less than 1, we can actually fill in the rest of it all the way up to infinity like this. We're going to use polynomial long division. Now, what we're going to be dividing by is x squared plus 1. And what we're going to be dividing is simply 1. All right, now watch this. How many times does x squared plus 1 go into 1? Well, x to the negative 2 times, right? All right, so let's multiply this. We're going to get 1, and then we're going to get plus x to the negative 2. Subtracting that, we're going to get negative x to the negative 2. All right, how many times does x squared plus 1 go into negative x to the negative 2? Negative x to the negative 4 times. That's how many times. Multiplying it, we get negative x to the negative 2 minus x to the negative 4. Again, subtracting, all we'll end up with is x to the negative 4. And now you can see the pattern. This is going to be plus x to the negative 6th minus x to the negative 8th. So in other words, 1 over x squared plus 1, 1 divided by this, is equal to the sum as n goes from 1 to infinity of negative 1. Let's see, where do we start? We started at a positive value. So it's going to be negative 1 to the n plus 1 times x to the negative 2n. And this will converge. Oops, you guys can't see that. And this will converge for x greater than 1. Yeah, that's going to converge for x greater than 1. All right, so now let's go back to Desmos here. So what did we just say? 1 over x squared plus 1 is also equal to the sum as n goes from 1 to, and I'm just going to put in 100 here again, so, and then it's negative 1 to the n plus 1 times x to the negative 2n. Yep. See? We have the rest of the 1 over x squared plus 1 graph right here. And if we copy this down, we have the entire thing except at x is equal to 1. We have the whole graph of 1 over x squared plus 1 except for the x is equal to 1 part. Okay. So let's get rid of that graph right here. And it's equal to this. Put in infinity. And this is good for x greater than 1. Okay, so, all right, let me collect my thoughts here. What were we doing? Ah, yeah, that's right. We were actually interested in arctangent formulas. So again, let's just go ahead and integrate with respect to x on both sides. So we're going to integrate with respect to x on both sides. Okay. So on this side, you see, we're just going to get arc tangent x. Switching the integration and summation notations here. Anti-differentiating this is just going to give us x to the 2n plus 1 over 2n plus 1 plus c. Okay. And then we know that c is 0. Okay, what about on this side? Well, again, on this side, we're going to get arc tangent x again. And then we're going to get, let's see, we're going to, if we integrate this, we'll end up getting x to the 1 minus 2n over 1 minus 2n. And then, of course, plus c. Okay. Now, this doesn't work exactly like expected. Watch. Arctangent x. Let me show you the graph there of arctangent x. All right, so there's our arctangent x. Now, we would expect that it's going to look like this. But not quite. Not quite. This is actually plus pi over 2. Or plus c. And we can show that, let's see, if we plug in x is equal to 0, well, what do we actually get if we plug in x is equal to 0? Well, we get 0 for arctangent x, but 0 to the 1 minus 2n. Well, that's equal to 1 over 0 to the 2n minus 1. Okay. Well, where does our n start? Let's see. If we plug in x is equal, yeah, okay, so now we have a problem. Now we have a problem. Because for any value of n, we're actually going to get 0 raised to a positive value over here, which is going to, we're basically going to get infinity here. But there is a way you can work it out to show that this is actually going to be plus pi over 2. I'll leave it as kind of like a side challenge there to prove why this is actually plus pi over 2. But in any case, we have this. Arctangent x is also equal to this sum. Okay, and this is good for x greater than 1. So we have the entire arctangent function defined for all values except at x is equal to 1. All right. So now, let's see. We don't actually have arctangent x. What we have is arctangent ix over x. So let's just divide both sides of both of these equations by x. All right. What happens here is we just get rid of that plus 1. what happens here is we get rid of this 1, but we also have to divide this pi over 2 by x. Don't forget that. Okay, but we still, let's see. Let's divide both sides by I. Okay. So now we have 1 over I. And then 1 over. And now let's take x on both sides to be ix. Okay. So on this side, we get ix. And on this side, on this side, we also get ix. Okay. Now we're taking x to be ix. Oh, we also have to take x to be ix here. Ix, right? Okay, x is ix on both sides. Ix. Okay. Not done. Ix. All right. Now you'll notice that this is just going to become negative x. So we'll put that negative outside. And the same thing's going to happen here. Negative x. All right. Now we can split this up into I to the 2n times x to the 2n. Okay, this is going to be I squared to the n. I squared is negative 1. That's negative 1 to the n. Negative 1 to the n. Negative 1 to the n times negative 1 to the n is 1. So we just have this. All right, what happens on this side? The same thing is going to happen. This is just going to be, let's see, x to the negative 2n times I to the negative 2n. Okay, that's going to be I to the negative 2 to the n. I to the negative 2 is 1 over I squared. That's 1 over negative 1. That's negative 1. That's negative 1 to the n again. Okay. So we have a negative 1 to the n. All right. This is negative 1 to the n times negative 1. So I'll write that. That's negative 1 to the n times negative 1. Again, negative 1 to the n times negative 1 to the n is just 1. All right. Now let's clean this up a little bit. Let's go ahead and let's see. Let's multiply. Well, let's see. 1 over I. What's 1 over I? That's negative I, right? Again, this is 1 over I, which is just negative I. Okay, now let's multiply both sides by a negative. All right, great. Okay. All right. So now let's rewrite this. The imaginary part of arctangent of Ix from 0 to infinity. Well, that's going to be equal to the imaginary part of two separate integrals. One going from 0 to 1, and one going from 1 to infinity. All right. So let's see. let's go ahead and paste that down there. And now, oh, we need to take care of this. Okay, again, this is just going to be negative I, and then we multiply both sides by a negative. Okay. All right, so we have this equality for x less than 1. And we have this equality for x greater than 1. I think I forgot to cancel out an I here. There should not be an I there. Yeah. Go ahead and rewind the video. That I right there should have actually canceled out. Because don't forget, there was an I here, and there was an I here. And then we multiplied both sides by I to get an I outside here. And that I would have canceled this I. And in fact, that should be a negative. Okay. All right. Hold on one second. Yeah, I just went ahead and checked that, and this is actually the correct identity. Um, like I said, I forgot that I had already had an I here and then multiplied by I. So in any case, now we're here. We're back to here. So what we end up with is we can change this to, well, now that we have arctangent of ix from, or for x less than 1, we can plug that version of it into here. And for the version for x greater than 1, what we can do is plug in this. All right. Now we're taking the imaginary part of both of these. So let's see. Well, we don't need the imaginary operator on this anymore. That's just going to go away. All right. Now, taking the imaginary part, this is going to go away. And this is purely real, so it will also go away. And we no longer need the imaginary operator. All right. Now, let's just check to see if this is true. So originally we were saying that this is true, right? We actually already showed it. Um, so let's actually see if this is equal to pi squared over 4. So I'm going to plug in some. We'll just go to 100, and then type in pi squared over 4. Yeah, so it is. I mean, obviously, if we took this to infinity, it would go to pi squared over 4. All right, so what we've said is that the imaginary part of this is equal to pi squared over 4, and it's also equal to this. All right. Let's clean this up a little bit. Let's interchange our integration and summation notations here. And evaluating this one is pretty trivial. We're going to get x, we're going to get 1 over n, we're going to get 1 over 2n plus 1 squared. So that's 1 over 2n plus 1 all squared. Okay, now this one is a little bit more difficult. Let's clean it up a little bit. Let's just bring this -1 out as a negative. Okay. Now, let's bring this 1 over 1 minus 2n outside. All right. Now this integral right here is going to give us x to the 1 minus 2n over 1 minus 2n from 1 to infinity. All right, our infinity term comes first. Well, don't forget, our index on n starts at 1 here. So we are always going to have a negative value here. So if we take infinity to a negative exponent, we get 0. So this whole term is going to drop out. Minus the x is equal to 1 term. So we're just going to be left with this, 1. Okay. So this integral right here is just equal to this. So let's copy that and paste it right here as a multiplication. Okay. All right, and then we'll bring out the negative to make this plus. All right. Oh gosh, what are we going to do now? Well, notice we don't have our indexes starting at the same place. Okay? So what we can do is let's subtract 1 from our n, and we will add 1 to our n. So we get n plus 1. N plus 1. Now let's distribute that. That's going to give us 2n minus 2, right? So that's going to give us minus 2n minus 1. Minus 2n minus 2. And again, that is going to give us minus 2n minus 1. Minus 2n minus 1. But, of course, that is just negative 2n plus 1. And that is also negative 2n plus 1. Negative and a negative cancel out. And now we are just left with 1 over 2n plus 1 all squared. And that is just equal to, these two things are the same thing, so we just have 2 of them. All right, so we're done. We proved that the imaginary part of this is both equal to pi squared over 4 and 2 times the sum of the reciprocals of the odd squares. So what this means, what we've just proved, as far as I know, this is a new way of proving this. We just proved that the sum of the reciprocals of the odd squares is equal to pi squared over 8. All right, guys, that was a long video. If you stayed with me this whole time, thank you very much, and we will see you next time.